watching Saturn right now that should not exist. Not the way it does, not doing what it does. By every rule planetary scientists spent 2 centuries refining, this world should have died before the first fish ever swam on Earth. It is smaller than the state of Arizona. It orbits nearly 1 billion miles from the Sun. Its surface temperature plunges to negative 223 degrees Celsius, cold enough to freeze carbon dioxide solid, cold enough to make Antarctica feel tropical. For over 200 years, that is exactly what astronomers believed it was. A frozen, inert, forgotten little moon drifting silently through the outer dark. Then a spacecraft flew past it and saw something that broke the model entirely. Columns of water, erupting from cracks in the South Pole, blasting ocean material into space at over 800 miles per hour. The moon was not dead. It was screaming, venting the contents of a hidden sea through fractures in its ice shell and hurling that water into the cosmos. Everything scientists thought they understood about small frozen worlds collapsed overnight. Not gradually, not reluctantly, overnight. If the kind of discovery that rewrites textbooks and reshapes our understanding of where life might exist makes your brain light up, subscribe. We go deeper every week. Now let us go to Enceladus. Look at a list of Saturn's moons, and you will find Enceladus buried in the middle, unremarkable, easy to skip past. Not the biggest, not the most dramatic, not the most famous. Just another name on a roster of over 140 frozen satellites circling a gas giant nearly 1 billion miles from the warmth of our Sun. It measures roughly 500 kilometers across, small enough to fit inside a single American state. Its surface is coated in water ice so pure and so reflective that it bounces back nearly all incoming sunlight, making it the most reflective body in the entire solar system. Its surface temperature in the coldest regions hovers near negative 223 degrees. No atmosphere worth mentioning, no obvious volcanic drama visible from a distance. For most of the history of modern astronomy, Enceladus was exactly what it appeared to be, a tiny ball of ice, silent, passive, dead. And that assessment made perfect sense. A body's ability to stay geologically active depends overwhelmingly on its size. Larger worlds retain internal heat longer because their volume to surface area ratio slows the rate at which energy escapes into space. Earth, at nearly 13,000 kilometers across, still has a molten mantle driving plate tectonics and volcanic eruptions 4.5 billion years after it formed. Mars, roughly half Earth's diameter, went geologically quiet billions of years ago. Its core cooled. Its volcanoes stopped. Its magnetic field collapsed. The pattern is clean and well understood. Small bodies cool fast. They lose their internal heat within a few 100 million years. Once that heat is gone, geological activity ceases. The world becomes a frozen fossil of its own formation. It dies. Enceladus is roughly 13 times smaller than Mars. By every reasonable calculation, it should have frozen solid before complex life ever appeared on Earth. Its rocky core, estimated at roughly 350 to 400 kilometers across, should have cooled into a rigid, immovable mass early in solar system history. Whatever primordial warmth it carried from formation should have radiated away into the vacuum long ago. There should be nothing flowing inside this moon, nothing churning, nothing generating heat. Enceladus should be a geological corpse. This expectation was so deeply embedded in planetary science that nobody seriously questioned it for over 2 centuries. William Herschel discovered it in 1789 using a homemade 40-foot reflecting telescope in the English countryside. He noted its existence, recorded its orbit, and moved on. The name itself came from Greek mythology. Enceladus was one of the giants, a titan buried alive beneath the earth by Athena after his defeat in a primordial war. The ancients believed his restless, imprisoned body caused earthquakes and volcanic eruptions from below the ground. It is an almost eerie coincidence that a moon named for something raging beneath a surface turned out to contain exactly that. But for nearly 2 centuries after Herschel's discovery, nobody knew. Enceladus remained a faint dot in the eyepieces of even the world's most powerful telescopes. Too small, too distant, too cold to warrant serious attention. Then, in 1980 and 1981, Voyager 1 and Voyager 2 swept through the Saturn system and returned the first detailed photographs of Enceladus. The images were grainy by modern standards, but they contained something that did not fit. Parts of the surface looked wrong. Several regions appeared unusually smooth, with almost no impact craters visible. In a solar system where every small body had been battered by billions of years of meteorite bombardment, a smooth surface was a red flag. Impact craters accumulate over time. The fewer craters you see, the younger the surface must be. Some terrain on Enceladus appeared geologically young, perhaps only a few 100 million years old. For a moon this small, that should have been impossible. Scientists published cautious papers speculating about possible resurfacing mechanisms, but without better data, the anomaly remained a curiosity rather than a crisis. Enceladus went back to being a minor moon with a peculiar surface. Interesting, but not urgent. It would take another 2 decades and a far more capable spacecraft before the truth detonated across planetary science. The Cassini spacecraft arrived at Saturn on June 30th, 2004, after a nearly 7-year journey from Earth. Built jointly by NASA, ESA, and the Italian Space Agency, it was the most sophisticated robotic explorer ever sent to the outer solar system, carrying 12 scientific instruments designed to study Saturn, its rings, and its moons in extraordinary detail. Its companion probe, Huygens, descended to the surface of Titan in January 2005 and returned the first images from the surface of any moon in the outer solar system. Cassini itself would remain in orbit around Saturn for 13 years, conducting 23 targeted flybys of Enceladus. Nobody expected Enceladus to be the mission's most important discovery. Titan was the star attraction, a world larger than Mercury with a thick nitrogen atmosphere, methane lakes, and complex organic chemistry. Enceladus was on the schedule, but it was not the priority. It was too small, too simple, too dead. The first close flyby in February 2005 was planned primarily to improve orbital models and test instruments. It was almost routine. Almost. On that first pass, Cassini's magnetometer detected something that immediately raised alarms. The magnetic field around Enceladus was being distorted in ways that suggested the moon was interacting with Saturn's magnetosphere far more strongly than a small, inert ice ball should. Something was generating a cloud of charged particles around this moon. Something was actively producing material and releasing it into space. The July 2005 flyby changed everything. Cassini dove to within 173 kilometers of the surface, and its instruments recorded data that would ultimately rewrite textbooks. The composite infrared spectrometer detected anomalously high temperatures along 4 roughly parallel fractures near the South Pole, each approximately 130 kilometers long and spaced about 35 kilometers apart, radiating heat far above the background temperature of the surrounding terrain. Scientists named them the Tiger Stripes. Temperatures along those fractures reached as high as -93 degrees Celsius in localized spots. That might sound brutally cold by human standards, but on a world where the average surface temperature hovers near -200, reading -93 is volcanic. Something beneath those fractures was generating heat and pushing it toward the surface. Something active, something ongoing. But the temperatures were only the beginning. The Tiger Stripes were not merely warm, they were erupting. Towering columns of fine ice particles and water vapor were shooting upward from the fractures into space, forming a vast plume visible against the blackness when backlit by the sun. The plume extended hundreds of kilometers above the South Pole, a feathery, radiant spray of material escaping the moon's weak gravity and streaming outward into Saturn's orbital environment. This was not a subtle observation requiring careful statistical analysis. This was an eruption visible in photographs. Enceladus was actively venting material into space, in real time, powered by an internal energy source that should not exist. The word that kept appearing in mission reports and press conferences was impossible. Not technically impossible, the evidence was right there in the instruments, but impossible in the sense that the existing mental model of what a moon like this should be could not accommodate what Cassini was seeing. Over the following months and years, Cassini returned for closer and more targeted flybys. Each pass brought new instruments to bear, and each set of results deepened the shock. The ion and neutral mass spectrometer sampled the plume directly and identified its composition with increasing precision. Water vapor dominated, as expected, but mixed into that vapor was a cocktail of molecules telling a far more complex story. Carbon dioxide, methane, ammonia, molecular hydrogen, and simple organic compounds. And then came the salts. Sodium chloride and potassium chloride, the same salts that make Earth's oceans salty, were embedded in the ice grains being ejected from the fractures. That was the turning point. You do not get sodium and potassium salts from sublimating surface ice. You get them from liquid water that has been in prolonged contact with rock. The chemical signature was unmistakable. Somewhere beneath the frozen surface of Enceladus, liquid salt water existed. Not as a theoretical possibility, the salt was right there, embedded in ice grains that Cassini's cosmic dust analyzer caught and measured as the spacecraft flew through the plume at over 7 kilometers per second. Enceladus had an ocean. More than 100 individual geysers were eventually identified along the tiger stripe fractures. The total mass ejection rate was estimated at roughly 200 kilograms per second. Every single second, 200 kilograms of water vapor, ice crystals, salts, and organic molecules launched off this tiny moon and hurled into space. Some material fell back as fresh snow, building up deposits hundreds of meters thick around the South Pole. The rest escaped into orbit around Saturn, spreading out to form and continuously replenish Saturn's E-ring, a faint but vast ring of ice particles encircling the entire planet. This single discovery answered a question that had puzzled astronomers for decades. Saturn's E-ring had long been unusually broad and diffuse, and without a continuous source of fresh material, it should have dissipated long ago. Enceladus was that source. Even the moon's legendary brightness, it reflects over 99% of incoming sunlight, making it the most reflective body in the solar system, turned out to be a consequence of its internal activity. A continuous rain of ultra-fine ice particles from its own plumes, coating the surface in perpetual fresh snow. Nothing about Enceladus was passive, nothing about it was dead, but knowing that Enceladus had an ocean immediately raised a question even more urgent than the discovery itself. How? What engine was running beneath that ice? The critical breakthrough came from gravity science. During close flybys, Cassini's radio signal was tracked from Earth with extreme precision, and tiny frequency shifts in that signal revealed the distribution of mass inside the moon. The results published in 2014 revealed a gravitational anomaly beneath the South Pole, consistent with a body of liquid water roughly 10 kilometers deep. But the gravity data told only part of the story. Researchers studying Cassini's imaging data noticed a slight wobble in the moon's rotation, larger than it should have been if the ice shell were frozen solid all the way to the rocky core. A team led by Peter Thomas at Cornell University spent years tracking the precise positions of surface features across hundreds of Cassini images. The final result, published in 2015, showed a wobble amplitude of approximately 0.12 degrees. Small as that sounds, when the researchers plugged it into structural models, the implications were stark. No plausible arrangement of solid ice connected to solid rock could produce a wobble that large. The ice shell had to be floating on liquid, not a regional sea beneath the South Pole, a global ocean. A world-encircling body of liquid salt water wrapping the entire moon from pole to pole, hidden from view but announced through columns of vapor and ice erupting through its southern crust. Enceladus was not a frozen moon with a warm patch, it was an ocean world with an ice roof. The thickness of that roof varies. Based on Cassini's combined data, the ice shell runs roughly 5 kilometers thick at the South Pole, where tidal heating is most intense, and over 20 kilometers thick at the equator and North Pole. The ocean beneath averages roughly 25 to 30 kilometers deep, sitting atop a rocky core approximately 350 to 400 kilometers in diameter. A rocky center wrapped in a global saltwater ocean, wrapped in turn by a shell of ice. The whole system continuously warmed from within by a gravitational engine that has been running for billions of years. That engine is the gravitational relationship between Enceladus, Saturn, and a neighboring moon called Dione. Enceladus does not orbit Saturn in a perfect circle. Its orbit is slightly elliptical, meaning the distance between the moon and the planet varies throughout each 33-hour orbital period, swinging from roughly 236,900 kilometers at closest approach reach to roughly 239,200 kilometers at its most distant. Saturn is 95 times more massive than Earth, and gravitational force follows an inverse square relationship with distance. Even this small variation in distance produces significant variation in the gravitational pull Enceladus experiences. As the Moon moves along its elliptical orbit, the near side gets pulled harder than the far side when close to Saturn, creating a stretching effect. As Enceladus swings farther away, the distortion relaxes. Every 33 hours, this Moon is squeezed and squeezed again. The effect is like repeatedly kneading a ball of bread dough. Every compression and extension cycle deposits a small amount of energy into the material as friction, and the dough gets warmer. Do it fast enough and long enough, and the heat accumulates. Enceladus has been experiencing this gravitational kneading for billions of years. Every orbit generates friction inside the Moon. Every cycle converts a tiny fraction of orbital energy into thermal energy. Accumulated across geological time, the effect is staggering. The tidal distortion amounts to perhaps a few meters of displacement across the entire body, a bulge so subtle that standing on the surface you would never perceive it. But a few meters of displacement distributed across the entire volume of rock, ice, and liquid water represents an enormous amount of mechanical work, converting orbital motion into heat at every grain boundary, every crystal lattice, every current in the intervening ocean. The orbit does not simply circularize and shut the whole process down, which it should have long ago because Dione is there. This neighboring moon orbits Saturn at a greater distance than Enceladus, and the two are locked in a 2-to-1 orbital resonance. For every single orbit Dione completes, Enceladus completes exactly 2. Every time the moons reach the same relative position, Dione gives Enceladus a small gravitational nudge that prevents the orbit from circularizing. The resonance continuously pumps eccentricity back into Enceladus's orbit, counteracting the circularizing effect of tidal friction. The eccentricity drives tidal heating. The tidal heating dissipates orbital energy. The resonance with Dione replaces that energy, a self-sustaining loop of gravitational energy that has kept this tiny ocean warm for billions of years. The result, measured by Cassini over 13 years, is a combined heat output of approximately 54 gigawatts, equivalent to the total electrical generating capacity of a medium-sized industrialized nation, enough to run approximately 54 nuclear reactors simultaneously. And none of it is stored heat slowly leaking out from ancient times. This is energy being actively generated right now, inside a moon that has no business producing it. From Oxford University, the Southwest Research Institute, and the Planetary Science Institute added a remarkable new dimension to this picture. By reanalyzing archived infrared measurements from Cassini's composite infrared spectrometer, the researchers detected excess heat at the North Pole of Enceladus, surface temperatures approximately 7 Kelvin warmer than they should have been if the only heat source were sunlight. On a world where the baseline hovers near -200 degrees, 7 extra degrees is an enormous anomaly. The only plausible explanation was heat leaking upward from the ocean through the ice. The same process driving the southern plumes, now confirmed operating simultaneously at the opposite pole. The measured heat flow at the North Pole came to approximately 46 milliwatts per square meter. The average for Earth's continental crust is 65. A frozen moon 500 kilometers wide is radiating heat at roughly 2/3 the rate of a typical patch of Earth's continental surface. When the North Pole heat flow was added to the South Pole measurements, the total reached approximately 54 gigawatts, remarkably close to theoretical predictions, implying approximate thermal equilibrium. Heat generated by tidal flexing roughly equals heat radiated away. The ocean is not a transient feature. It is not the last gasp of a dying world. It is a sustained, long-term environment maintained by a gravitational engine that shows no signs of stopping. Now we reach the part of the story that makes this more than a tale of surprising geology, because Enceladus's ocean does not just contain water, it contains everything. The rocky core of this moon sits in direct contact with the liquid ocean above it. There is no high-pressure ice layer in between because the moon's gravity is too weak to produce one. Liquid water has been touching silicate rock across the entire ocean floor for billions of years, with continuous heat being supplied from below. On Earth, the places where hot water interacts with rock on the ocean floor are called hydrothermal vents, and those environments support some of the most biologically productive ecosystems on this planet. Communities of microbial life functioning entirely independent of sunlight, drawing energy from chemical reactions between water and rock. The evidence for active hydrothermal processes on Enceladus's ocean floor is some of the most elegant detective work in modern planetary science. In 2015, a team studying Cassini data traced the origin of nanoscale silica grains found in Saturn's E-ring. These particles, between 6 and 9 nanometers in diameter, composed almost entirely of silicon dioxide, form through only one known mechanism. When hot water saturated with dissolved silica encounters a sudden temperature drop, the silica precipitates as ultrafine grains. The 6 to 9 nanometer size range corresponds specifically to water temperatures of at least 90 degrees Celsius, dropping rapidly to near freezing conditions. That meant somewhere on the ocean floor of Enceladus, water was being heated to at least 90 degrees through contact with rock, dissolving silica from mineral surfaces, then rising into cooler ocean water where the silica precipitated as nanoparticles, got entrained in the currents feeding the plumes, and was ejected into space, where Cassini caught them. A message sent from the ocean floor of Enceladus, through the ice, across the vacuum of space, into the instruments of a spacecraft, in the right place at the right time to intercept it. There is hot water touching rock at the bottom of this ocean, right now. Then came the molecular hydrogen. Cassini detected it during its deepest plume dive in October 2015, passing within 49 kilometers of the South Pole surface. The concentration was higher than could be explained by simple decomposition of water molecules. The most likely source was serpentinization, an ongoing chemical reaction between liquid water and iron-bearing minerals in the rocky core, in which water infiltrates cracks in certain rocks, reacts with iron in the minerals, and liberates hydrogen gas. On Earth, serpentinization is one of the primary chemical engines driving hydrothermal vent ecosystems. The hydrogen it produces serves as fuel for chemosynthetic microorganisms, bacteria and archaea that harvest chemical energy to drive their metabolism, completely independent of sunlight. They live on rock, water, and chemistry alone. Finding molecular hydrogen in Enceladus's plume was equivalent to finding smoke rising from a chimney. It did not prove there was a fire, but it proved there was heat, there was fuel, and there was an active chemical process capable of sustaining one. Then came the organics. Cassini's cosmic dust analyzer caught ice grains with molecular masses exceeding 200 atomic mass units. Not simple molecules, but large, complex compounds, with structures suggesting they had formed through sustained chemical processing in a liquid environment. Compounds with oxygen-bearing and nitrogen-bearing functional groups, the hallmarks of the chemistry that underpins biology. The range that on Earth includes amino acids, fatty acids, and the molecular building blocks of cells. Then came the phosphorus. For years, Cassini had detected carbon, hydrogen, nitrogen, oxygen, and sulfur in the plume, 5 out of the 6 elements universally required by life as we know it. 5 out of 6 was extraordinary, unprecedented for any world beyond Earth. But 5 out of 6 nagged at astrobiologists. Phosphorus is the backbone of DNA and RNA, the energy currency of every living cell in the form of ATP, and a major structural component of cell membranes. Remove phosphorus and the architecture of life, as biology understands it, collapses completely. In June 2023, a team led by Frank Postberg at the Free University of Berlin published a result in the journal Nature that eliminated the anxiety. By reanalyzing archived Cassini data from Saturn's E-ring, the researchers identified sodium phosphate in the ice grains. Phosphorus, not a trace, not an ambiguous signal. Phosphorus dissolved in the ocean at concentrations estimated to be at least 100 times higher than in Earth's oceans. Enceladus was not merely phosphorus-bearing, it was phosphorus-rich. The geochemical models that had predicted phosphorus scarcity turned out to be based on assumptions that did not apply to Enceladus's alkaline, carbonate-rich conditions. In that specific chemical environment, phosphorus remains highly soluble. 2.